Okay, so in today's session, we will discuss something about ping and ARP. Okay, how ping works, how ARP works, and basically that is what in many of the interview questions this is asked. Can you explain the working of a ping, or can you explain how ARP works? Or sometimes when they ask you, can you explain the flow of the packet from point A to point B, right? So they are expecting all this information, like in that packet flow, explain the ARP function, explain the ping function, etc. So it may be a one-on-one question about ping and ARP, or it can be a mixed question like explain the packet flow. So we will try to understand that with the time that we have in hand. But before we jump into that discussion, okay, because when I explain ping and ARP, I would be explaining the different fields when we are trying to ping from point A to point B, right? Give me a minute. So when I'm explaining ping and ARP, as I said, I would be explaining the headers inside the ping and ARP, right? So before we try to get inside ping and ARP, as I said, I would be explaining about headers. So let's start to understand what is a header and what are the what is the format of a header, especially the Ethernet header in layer 2 and an IPv4 header in layer 3. So we'll start our discussion for today's class with that. So starting with the layer 2 header, or in other words, we call it as the Ethernet header. Now the Ethernet header, okay, it consists of a lot of information. So before we even try to get inside that detail, let's first understand what is a header. First of all, when we someone says, explain me the header, what does it mean? So header is nothing but another word for format. Okay. So whenever we write a letter to someone, right, we write it with a format. We write it with a to address, then we have the from address, then we have the date, the subject of the letter, then we have the body or the content of the letter, and then we have the salutation like yours faithfully, thankfully, etc. like that. And then we have our name, and if it's a very official letter, we also have a signature. Right? If it's an unofficial letter, we usually do not write. We do not put a signature. So this is a basic format of writing a letter. And in this format, if you miss any header or any point or any format of this header, or if you miss this template, your letter basically becomes incomplete. So let's say if I miss to write, for example, if I miss to write the subject for the letter, whoever is reading that letter will not get an idea what is this letter about, right? So basically, it's an incomplete letter. Anyway, when he or she reads the body of the letter, he'll come to know. But as per the format of the letter, the subject is always required. Or for example, if the date part is missing, right? So whoever receives the letter, he will not know when was this letter sent or when was this letter written, etc. Right? So such kind of small details or format is required in order for a person to understand the letter. Similarly, in an Ethernet layer also, or an Ethernet packet, it has its own format, right? And until and unless all the details in that format is there, any networking device, a switch, a router, a PC, a printer, a server, anything, any networking device, if it does not find all the information in the layer 2 header, it will be incomplete and it will not be able to understand or process that data. Okay, so let's get inside that format and what are those format and what does it mean? Let's try to understand. So the first field in the Ethernet header is called as a preamble field. Okay, preamble field. And then we have something called as SFD, which is called as start frame delimiter. Then we have the destination MAC address, then the source MAC address field. Okay. Then we have something called as the type field. Then you have the data, right? And then you have the frame check sequence, FCS. So this is what your uh, basic Ethernet header would look like. Again, I'm not involving VLAN into this. This is a Ethernet header without VLAN. And in our discussion about VLANs, we saw such Ethernet format where VLAN was not present. So consider this as that format. Okay. Now, preamble is actually a 7-byte field. Okay. Preamble is a 7-byte field. SFD is a 1-byte field. Okay. And destination MAC, source MAC, we know that 6-byte, right? There, it is a 48-bit destination MAC and a source MAC. So 6-byte each is also 6-byte. Okay. Let me check what is a type field. What's the size of the type field? Give me a minute. So 2 bytes and 4 bytes. So this is a 2 bytes field, right? And frame check sequence is a 4-byte field. And this data field, as you can see, it varies between 46 to 1500 bytes. Okay, 46 to 1500 bytes, depending on what kind of data are you getting. So let's get into the details of each and every field. So the first field, preamble. Okay. What is the use of preamble and what is the format? Preamble has its own format also. Okay. So as I said, preamble is a 7-byte field. Out of these 7 byte, let's check first byte or 1 byte of it. 1 byte of this preamble field consists of alternate ones and zeros in this format: 1 0 1 0 1 0 1 0. This is 1 byte or 8 bits. Okay. Now, all the 7 bytes of this preamble field, please listen to this very carefully. All the 7 bytes of this preamble field is exactly similar. So yeah, second byte, third byte, fourth byte, fifth byte, sixth, and seventh byte of your preamble field is exactly 10101010. Right. So basically, you will have 7 bytes, right? 1 byte is equal to 8 bits. So you will have 56 bits of ones and zeros. 56 bits of ones and zeros continues. So if you open up a preamble, if you open up a layer 2 header, okay, if you open up a layer 2 header, uh, uh, in if you capture a layer 2 header and open up its preamble field, this cannot be seen in Wireshark. Okay, even if I try to show it in Wireshark, I can capture the data on Wireshark, but preamble field is usually excluded in the Wireshark. Okay, but if you check this in Packet Tracer, if you just do a simple practical on Packet Tracer with the example of VLAN, you will see the preamble field with ones and zeros. So the first 56 bits of your Ethernet header is ones and zeros, alternate ones and zeros. All right. Now, the second field, that is SFD, which is also called as start frame delimiter. Start frame delimiter. Okay. This is a 1-byte field and is also very similar to the preamble field 10101010. However, the last bit of the SFD is not 0, it is 1. So in continuation with your preamble field, right? In continuation with your preamble field, this 56 plus 8 bits, which is which is 64, right? So your 64 bits, 64 bits of your Ethernet header, the first 64 bits, not first 64, 63 bits. The first 63 bits of your Ethernet header is alternate ones and zeros. And the last bit, the 64th bit, is 1. Okay. Now, what is the significance of this? But before I move on to the significance, any problem understanding the format of preamble and SFD, start frame delimiter? Anyone?
No, but why we need preamble? That
Yeah, I'm coming to that point. But any
okay.
problem with
Then
the format? Anyone?
no.
All right.
Actually,
So
Lakshya, this total Ethernet header is of how much byte?
okay, so you total Ethernet header, you can say 8 plus 12, 20, 22, 22 plus 4 is 26. Now, 26 is your constant field. Okay, 26 bytes is your dedicated size. Now, the data, it depends on your data. So minimum data that you can have is 46. So 26 plus, is it 20, did I calculate it right? 7 plus 8, 6 plus 6, 12, 8 plus. Yep, 20, 22, 24. Yeah, sorry, 24. 24 plus 46, we get 70. Okay, so your minimum size of your Ethernet header is 70. Okay, minimum size is 70. Now, if you have more data, it may go even beyond that. Okay, so 1500. 1500 is your maximum byte. So 1500 plus your normal Ethernet header, 24. So 1524. So your Ethernet header size varies between 70 plus 70 and 1524 bytes. It varies. Got it? So the 24 bytes that I calculated are the preamble, SFD, destination map, source map, type field, and FCS. These are always constant in every Ethernet header. Every Ethernet header will have these fields, and they will occupy only this much size of your Ethernet header. So 24 bytes is always constant. Now 24 bytes is always constant, plus the minimum data size that you will have is 46. Okay, so add 46 over here and you get 70. So your minimum size of your Ethernet header is 70. Then if you have 1500 bytes of data, right? If you have 1500 bytes of data and your dedicated 24 bytes over here, if you add them, so you get 1524 bytes. So your minimum Ethernet header size is 70 and the maximum that it can go is 1524 bytes. Clear? Okay. Now coming back to our discussion on preamble and SFD, we understood the format of the preamble and SFD, that they are alternate ones and zeros. But what is the significance and why do we need it in an Ethernet header? Now consider two switches. Switch 1, okay, with a MAC address of 1111, and switch 2 with a MAC address of 2222. Okay. Now consider switch 1 is sending data to switch 2, or switch 2 is sending data to switch 1. They are sending data to each other continuously. Okay. So let's say switch 1 sent frame number 1. Okay. Then frame number 2. Then frame number 3. Then frame number 4. Okay. 4 continuous frames is sent by switch 1 towards switch 2. Okay, is everyone on the same page with me? Is everyone clear with the situation that we have in hand? Switch 1 is sending information to switch 2. Switch 1 has sent 4 frames to switch 2. Frame 1, 2, 3, and 4. All right. Now, think from this perspective. All the frames that is sent by switch 1 to switch 2 will have the exact same information. Switch 1, switch 2, switch 3, and switch 4 will have the same preamble field, will have the same SFD field, will have the same source MAC address, that is destination MAC address 2222, will have the same source MAC address 1111, will have the same type field. We'll come to the type field in some time. Type field will also have the same data, assuming the data is same, and will also have the same frame check sequence header also. Now, this is frame number 1. Frame number 2 will also have the same field. Frame number 3 will also have the same field, exactly same. I'm not saying similar, exactly. It's a replica. Okay, and 4th frame will also have the same field. Now, think from switch 2's perspective. Please understand, all the networking device, they see these data. As human being, we know this is SFD, this is 222, this is 11, this is type data and FCS field. But from a switch's perspective or from a networking device's perspective, it's an electronic device. And we know that all the electronic device understands only ones and zeros. They understand only ones and zeros. Eventually, what would happen in their IC or the integrated chip, these information that switch 1 is sending to switch 2 is eventually converted into ones and zeros. Now comes the problem. As I said, all the data in frame 1, 2, 3, and 4 is exactly the same. How is switch 2 going to differentiate that frame 1 is a different frame 2 is different from frame 3 is different from 4 is different from all the other frames? Is everyone clear with the problem over here? The problem is all the data, every data in each of these frames is exactly the same. How is switch 2 going to differentiate that frame 1, 2, 3, and 4 are all different frames? It is supposed to, switch 2 is supposed to treat these frames differently. Is everyone clear with the problem? Srinivas, Tarun, Vivek, are you guys clear with the problem here?
Yes.
All right, thanks. Right. So this is where your preamble and SFD fields come into picture. So let's say switch 2 received frame number 1. Switch 2 received frame number 1. It read the preamble field, SFD field, destination MAC, source MAC, type, data, and frame check sequence. Right. As I said, switch 2 is receiving these frames in continuous manner. Now, after reading FCS field, right, frame 2 is in the wire. Frame 2 has been received by switch number 2. Now, how is switch 2 going to differentiate frame 1 and frame 2? With the help of preamble and SFD. So as I said, in every Ethernet header, preamble and SFD field are the first 2 headers that any networking device will read. And what is that? Continuous ones and zeros. For 63 bits, it will read continuous ones and zeros, and the 64th bit will be 1. So when any networking device reads such a format of continuous ones and zeros, and the 64th bit as 1, it understands that a new frame is coming. That is what the name says here. Start frame delimiter, meaning a new frame is about to start. A new frame is about to start. So with the preamble field, it gave an indication that continuous 56 bits of ones and zeros are there. Then start frame delimiters field starts with again continuous ones and zeros. However, the last bit is 1. When any networking device reads such a format, it understands that the old data is over and the new data is being received. A new frame is about to start. And in that new frame, the first field that it is about to read is the destination map field. Then again, frame 2 is getting over. Frame 2 is over. Frame 3 is starting. How is switch 2 going to differentiate? Again, in frame 3 also, it will also have continuous ones and zeros, and the 64th bit is going to be 1, indicating a start of a new frame. And that is with the destination map. Again, third frame is over. Switch 2 has read the third frame. Then fourth frame is starting. In the fourth frame also, it will also have continuous ones and zeros. Okay. And again, last 64th bit is 1. So your preamble and SFD field together helps a networking device understand that a new frame is now, the old frame is over, a new frame is incoming. Okay, old frame is over, the new frame is, you are reading the new frame, and after the 64th bit, the information about the new frame will start. Okay. Any question, problem understanding this part?
But in the fourth frame, the 64th bit should be 0, right? Because this is the last frame.
No, 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 no. It is the format. The format of SFD is 10101011. It is this format of SFD. The last bit is not 0, the last bit is 1.
Okay.
If
That is the
last
format.
bit set to 1 means it will think that next next frame also it will come like that, no?
No, no, no,
If
no,
it
no.
is set
See,
to 1 means.
not next frame. It is not talking about the next frame. See, this preamble and SFD is for this frame only. Okay, basically preamble and SFD is telling that your old frame is over. Whatever frame that you were reading is over. So before the fourth frame, it was reading the information about third frame, right? The last field of this third frame was FCS. In FCS also, it had alternate or combinations of ones and zeros. 101100001111, something like that, whatever be the combination, right? Once switch 2 completes reading the information of FCS, then suddenly it starts reading this preamble and SFD field for the fourth frame. So it understands that the frame, whatever information was being sent in the third frame is over. It has finished reading that information. Now it is supposed to read the information of the new frame, that is the fourth frame. So please understand, it's not just between two switches. Even with 3 different switches also, it's going to be the same thing. Let me add switch 3 here. Switch 3 is also sending information to switch 2. Switch 3 will also have the preamble and SFD field. Let's say, let me write this as frame 5, frame 6, for example. Okay. Now, let's imagine okay. So the first frame that switch 2 received was frame number 1 by switch number 1. Okay. The second frame that switch 2 receives is frame number 5 that is sent by switch number 3. Okay. Here also in frame number 5, it will have the preamble and SFD field, which will say 10, 10, 10 like that. And the 64th bit is going to be 1. Now, so switch 2 understands that the old frame that it was reading is over. A new frame is coming now. How does it know that a new frame is coming? Because it is reading continuous ones, a format of continuous ones and zeros. So now it is preparing. Basically, the header is telling the switch to prepare itself to read new information. To read new information. Okay, now when fifth frame is over, okay, when fifth frame is over, let's say switch 2 receives frame number 2. Frame number 2 will also have the same information where it says 10, 10, 10 continuous 1 zeros. That is the preamble and SFD field. SFD field's last bit is going to be 1. Okay, then the next is destination map. So what is happening? After the fifth frame's information is over, switch 2 is reading continuous ones and zeros format. So it is preparing switch 2's frame 2's preamble and SFD field is telling the switch to prepare itself to start reading new information. The old information is over. Now start reading the new information. In the new frame, what is the new information? With the new destination map and with the new source map. When this is over, frame 2 is over, let's say frame 6 is received. So frame 6's preamble field and SFD field will tell the switch to prepare itself to read new information present in this frame. And that new information will be a different MAC address, will be a different source MAC address, will be a different data type, etc. Is this clear now? What is the use of preamble and SFD field? Srinivas, Tarun?
I got it. Okay, I have to, I think, watch it again. That little
No,
bit confusion is there.
yeah, please feel free to ask now. It's okay. Where is the confusion? It's okay. Hello.
Hello.
Yeah. Please tell me your confusion. What is the confusion?
Okay. I got 90%. Okay. So every field, okay, it will be identified with preamble and SFD. Okay, that I understood. Mm, Anyways, the on that I think like it will be identified now from which switch it is coming based on the source and the destination address. No? Like from switch 3 also is there, right? Switch 3. Yes. Okay.
I'll tell you. See this. Convert this. Think and just imagine yourself converting this into the binary format. You know this is a hexadecimal form. This is a data. This is a real-time data that you see in front of you. These are all real-time data. Okay. And when a real-time data is converted, even this 01 BBC 74495 D8 is for our convenience. The real data, when you open up, the real data is read inside the integrated chip of any networking device, and it is read in format of ones and zeros. Imagine having so many data incoming on a particular switch, right? It may be from the same switch, it may be from different switches. how is that switch going to differentiate that it is receiving new, or is it reading the same frame, or is it reading a new frame? To remove that confusion, the preamble and SFD fields are present. Okay, so if you see this is just one. Okay, this is one frame, the data inside one frame, or one packet. Okay, this is data in another frame, this is the data in another frame. So imagine there are so many data that a networking device is reading. Currently we are thinking from only layer 2 perspective. In a matter of seconds, it is reading the physical layer, it is reading the physical layer, it is reading the layer 2 information, it is reading the layer 3 information and above, and everything is in ones and zeros. Now remove layer 3, layer 4, layer 5 information, just think from layer 2 perspective. See here, this is the layer 2 information that you see, and if I open the layer 2 information, and okay, it is not showing the data. What data is it carrying? Okay, so imagine if the switch has to read so many things in a matter of seconds. How is it going to differentiate that the old data is over? Or just think this perspective, this frame, that it has read the layer, it has read the physical layer, then it has read this layer 2, then it has completed reading the layer 3, then it has completed reading the layer 3, then it is moving to layer 4. How is it going to differentiate with all this information? So to ease up that work, okay, of differentiating the old frame with a new frame, preamble is actually helping the switch. Preamble and SFD are helping the switch to differentiate that the old frame is over. Now you're reading a new frame. So it's like, let's say you are receiving letters. Okay, you are receiving a letter. Okay, with two address, let's say from me. Okay, I am writing a letter to you. Okay, to let's say the interview batch. Okay, from Laksh. Okay, and I'm not just sending one letter. In just a second, I'm sending you, for example, 1,000 letters. Okay, I'm sending you information about 1,000 letters. You will not have time to read who is it coming from. Is it a new letter? Okay, let's say you started reading one letter. Okay, you read the subject, then you read the body of the letter, etc. All that body is basically the data. Okay, by the time you finish reading, right, regards Laksh. Okay, a new letter has come to you. You do not have the time to read this information to and from. There's so many letters. As I said, in 1 second, you're using 1,000 letters. By the time you finish reading the last word, that is Laksh, now you're reading the second letter. How are you going to differentiate? Is this the continuation? Is the first letter over? Or are you reading the same letter? Is this analogy related? Is this? Can you guys understand this analogy?
Yes, yes, yes. Like,
Right.
yeah.
So, yeah, go on. Yes, Srini.
Yes, like when we complete the first letter, no, so we have to understand the second letter. Like it is continuation of first one, or so something should be there on that first letter, like it is like continuous. So I think it will be here preamble and SFD doing like this one. I think for this purpose only.
Exactly.
Like
Exactly.
okay.
So For example, again, let me again give you the other example. Okay, I'm just writing random. Sorry. I'm just writing randomly. Okay, if there is no space, can you read these? No, until there is a space. Okay, you will not. You cannot differentiate if it's the same word or if it's a different word. So, what is that delimiter with which you are able to differentiate? It is the space, correct? So, whenever we write, right, we give spaces between words, right? So, let me write I am Laksh, right? So, instead of writing like this, okay, it's a three word sentence. You are able to make it. Okay, if I start writing I am Laksh, I so yeah, I work in Cisco. I have 10 years of experience. If I start writing like that, it's going to be very difficult for you to understand, right? So how can you understand this? Until and unless I give a space, right? Until and unless I give a space, it is not easy. Okay, now it is much more readable. That is what the start frame delimiter and the preamble are doing. They are basically creating a kind of a space between two different frames so that the switch is able to read these frames in a better way. It is able to differentiate that frame one is a different frame, frame two is a different one. Is this clear? Tarun, Vivek, Srinivas?
Yes, sir.
So that is the significance of your preamble and SFD field. Okay. Now, as I said, the format of preamble and SFD are ones and zeros. Please remember, it's a 7 byte, not 7 bit. It's a 7 byte, 7 bytes of preamble and 1 byte of SFD, where the last byte of SFD field is 1. Last bit of SFD is 1. We already know what is a destination map. We already know what is a source map. I'm not going to discuss about that. Now the type field. Type field. Now, let's say in a letter, okay, or whenever you are, yes, whenever you are receiving a parcel from Amazon, Flipkart, or whenever you send a parcel to someone, right? The courier company, right? The courier company mentions what kind of parcel is this. Is it an electronic parcel? Is it an electronic parcel? Is it a book? Right? Is it a dress? Right? Or is it a document? Something like that. So that whoever is receiving this parcel can understand what kind of parcel is it? Is it an electronic parcel, book, dress, or a document? Right? Even or whenever this parcel is being transferred from one location to another location, the people who are handling these parcels, they can easily identify, is it an electronic parcel? So they'll handle it carefully. If it is a book parcel, they'll even handle it carefully so that the book does not get bent. If it's a document parcel, then they should be sent to the receiver as soon as possible. All that information is mentioned, right, in that parcel. Similarly, in a layer 2 header, this type field in your layer 2 header tells what kind of layer 3 data is being carried. Okay, now we know that as per the OSR layer, we have layer 7, layer 6, 5, 4, 3, 2, 1. So in this layer 2, type field tells what kind of layer 3 information is it carrying. Is it carrying an IPv4 packet? Is it carrying an ARP packet? Right? Is it carrying an IPv6 packet? What kind of packet is it carrying? Type field mentions that. What kind of layer 3 data is being carried? Clear? What is the type field doing there? Any question? Now, data, we know what is a data. The data can be the information in the data is the information from layer 3, okay, or layer 4, or layer 5, or layer 6, or layer 7, right? So basically, all this information, whatever is being sent down from layer 7 up to layer 3 is basically your data. Okay, that is in the data field of your Ethernet. Then the last one is FCS, or the frame check sequence. Frame check sequence. Now, what is a frame check sequence? So by the name, we can already understand it is actually checking the sequence of frames. This is a general mnemonic that you can memorize to understand it better. Frame check sequence is actually checking the sequence of the frames. This is just a mnemonic, but the actual work is, let's say, switch 1 is sending a data to switch 2. Okay, when you connect these two switches together, right, they pass some information to each other through something called as CD. Like in Cisco switches, they transfer information through CD. Okay. Now, using that information, they create something called as a frame check sequence. So what is a frame check sequence? Now let's say when switch 1 is sending the frame, it runs an algorithm. I'm not sure what kind of algorithm it runs. Most probably it is running a hashing algorithm. You can read on Google what is a hashing algorithm. And don't worry, they are not going to ask you about hashing algorithm in the interview. So a frame check sequence. Switch 1 runs a hashing algorithm and it creates a value. Let's say for that hashing value, the value is 123. This value will be in the frame check sequence of your header. Then that frame is sent to switch 2. Switch 2, when it reads this frame check sequence, it will also run the hashing algorithm. Okay, and the value should come to as 123. When the value is same, the hashing algorithm value that is sent by switch 1 and the hashing algorithm value that is calculated by switch 2, both are same, that is 123 in this example. That means this frame that is sent by switch number 1 is error free. Okay, it is error free. Second, not corrupt. Not corrupt. Third, frame integrity is not compromised. Basically, compromised. Basically, no one has done anything with the frame. Okay, no intrusion, no security breach in that frame. If the frame check sequence that is created by switch 1 and the frame check sequence that is calculated by switch 2, both are same, That means the frame is not corrupt, it is secure. Now, if the frame check sequence is not same, let's say instead of 1, 2, 3 over here, it calculated as ABC. That means this frame that is sent by switch number 1 is corrupt. It may be compromised. It may have a data breach, some security problem. So switch 2 is not going to read the data field itself. Right here, this switch 2 is not going to open the data field. It is going to discard it. Now you may think, why is the data field not in the end? Because the data field is only there after the type field. It knows it's a data field. It is not going to read this data field unless the frame check sequence is okay. When the frame check sequence is okay, it opens up the data field. When it opens up the data field, it will read the layer 3 information. It can be an IPv4 packet, it can be an IPv6 packet, or it can be an R packet, anything. So this is the importance of frame check sequence to basically find out any errors or basically help the networking device understand there is no problem, there is no security breach, there is no data breach with that. Clear? Any question? Okay, any question with the layer 2 header?
That's fine, Laksh.
No.
Thanks. Now, moving on to the next header, that is the layer 3 header, and specifically we are checking the IPv4 header. IPv4. So let me first draw the IPv4 header format. The first one is your version. So let me go through this first. You have a version, header length, QoS or TOS, total length, identification field. These are flags called as a reserved flag, don't fragment flag, more fragment flag. Then you have fragmentation offset field, time to live, protocol field, checksum, destination IP, source IP, options field, and the data field. These are the fields in an IPv4 header. Okay. So before I jump, do you guys have any idea of any of these fields? What are these fields for, and what are the uses? Any, it's not necessary that you have to know every field. If you have knowledge about any of the field, please feel free to share.
I have idea on few fields,
Yeah, tell me.
like a header length and total length header, like version, like is it IPv4 or it will mention there, no? Or is it like
Yes.
IPv4 address or something?
Mm, mm,
Regarding the header length, like it will, when it is sending any packet right to the destination, it will mention that it is like 4-bit field, 4-bit I think. Okay,
mm,
maximum 15 I think. Okay, it will mention that what type of like total amount of data it is sending. So I think that
mm,
for identification field, it is like from source to, it is sending continuous packets right to the destination. A
yeah.
destination will identify that for like packets using this identification number,
Okay.
uh,
Mm, mm,
like so. And regarding fragmentation offset, not remembered, but like when more data uh, it has to send, but on the ethernet link it only supports what 1000 MB of data or something like
mm,
that. No, it will do fragmentation. So at that
mm,
time it
mm.
will, I think, fragmentation offset set to 1 or something like that. I mean, exactly I don't know, but yeah.
Yeah.
So protocol checksum, it is for, I think, security related for
Yeah.
destination source IP. We know that options. That I am not sure options. Data, I think
Yeah. Right.
random something like whatever data
Yeah.
coming
Yeah.
from the upper layers. So,
Right.
yeah.
Right. So many things you correct. You said partially correct. It's okay. Anyone else would like to give it a shot?
Yeah, the options are basically used for the extra features, which are, I mean, rarely used. If you are using QoS and if you have something else, and those things will come into the options field, I think.
Oh, yeah.
Rest,
Mm,
rest,
mm.
what Srinivasan told, it's like that only.
Oh, no problem. No problem. Okay. So the let's start. The length of your IPv4 header, first of all. Okay. Starting from here to here, it's actually 32 bits. Okay. It is 32 bits. Now, first, the version field. Because we are looking into IPv4, in this version field, it will have IPv4. And as I said, all the networking devices, they understand it in the binary format, in the form of ones and zeros, right? So for a networking device in an IPv4 header, how is it going to read the version is 4? It is going to read it in the binary format, and it is going to be written as 0100. This is the binary number for binary format for 4. And in every IPv4 header, you will always see this number only in the version field, indicating that it's a IPv4. Okay, if it's a V6, you will see 0110. Okay, 0110 is the binary format for 6. But for IPv4, we have 0100. And if we want, we can cross verify it with the wire. So IPv4 header, you can see version field, version it says 4, and the binary number is 0100. So 0100 is always what is always what you will find in the version field. Now the header length. Okay, header length is the minimum size of your IPv4 header. Is the minimum size of your IPv4 header that is supposed to be there, meaning that it is the minimum length of your IPv4 header. Below that number, your IPv4 header is incomplete. So just like your Ethernet frame, we calculated if we exclude the data field, the minimum length of your Ethernet header is 24 bytes, correct? Meaning that your preamble 7 byte, 1 byte, 6 byte, 6 byte, 2 byte, and 4 byte. This equals to 24 byte. So any value less than 24 bytes, if it is 23 bytes, that means this Ethernet frame is incomplete. The minimum requirement is 24 bytes. If it is below 24 bytes, that means your Ethernet header is incomplete. Similarly, for your IPv4 header also, this header length tells what is the minimum size of your IPv4 header, meaning that what are the fields, what are the mandatory fields that are supposed to be present in your IPv4 header to give it a minimum size. Okay, so the minimum size is 20 bytes. And how is that calculated? I'll also tell you. We know that the length of your of each layer in your IPv4 header is 32 bits. Okay, so how many, excluding your options and excluding your data field, how many rows do we have? 1, 2, 3, 4, and 5, right? So 32 bits into 5, you have 160 bits. You have 160 bits. Okay, to convert it into bytes, divided by 8, so you get 20 bytes. That is what this header length means. So in an IPv4 header, these 5 rows of fields should be present in your IPv4 header to call it a complete IPv4 header. You may not have any data, you may not have any options field, but the minimum requirement is that it should have 20 bytes of information. And how is it calculated? I just showed you. So we have 32 bits of length, and we have 5 different rows. So 32 times 5 gives us 160 bits. If you convert it into bytes, divided by 8, you get 20 bytes. And let me show you over Wireshark. You can see
I think header length should be
header
4 by
length.
4 bits, na?
Header length is 20 bytes.
Okay. 20.
20 bytes. Okay. Now the next field, QoS or ToS. What is this? So before we understand the size or what is it, we will see what does actually QoS mean. Quality of service or type of service, whatever you want to call it. QoS. So imagine this is a road. Okay, this is a road, and there are a lot of vehicles that are standing on the road, or you can think they are stuck in a traffic. They're stuck in the traffic jam, and corresponding to Indian roads, you do not follow any traffic rules or lane regulations. So just let me literally make it a traffic jam. Okay, so consider these are the vehicles and Indian road. Okay, now suddenly, let's say there is an ambulance here. Okay, which wants to move ahead. Okay, which wants to move ahead. Now, what is this ambulance going to do? If it wants to make a way in this traffic, what is it going to do? Can someone tell me? The ambulance is far behind and it wants to go as fast as possible in this traffic. What is it going to do?
We need to give priority, maybe.
Okay, but how ambulance is going to take that priority?
I think someone has to do no that. So
No,
that
no.
we can
Think
give
from
priority
this.
to them.
Think from this analogy. Think from this analogy. Ambulance is stuck in a traffic. Ambulance is stuck in a traffic, right? How is it going to make a way so that it can move faster in this traffic?
By clearing one side.
Again, same question. How is it going to do that?
It has to give signal, right? It will give signal, no?
Exactly. Right. That signal is basically the siren. Siren plus horn. Right. And it has a typical siren. We know that the traffic, not the VIPs or the ambulance or the fire trucks, right? They have special sirens, which are not regular sirens. So we know someone is behind us who is a special vehicle, not a regular vehicle. So when we see the siren and when we see the horn, right? What we do, we give a way to the ambulance so that the ambulance can move faster. Correct? This is what the siren does. So how is the ambulance taking that priority? Because first of all, it is a ambulance. Ambulance, fire trucks, VIP vehicles, they are given special priority. Okay. And how are they using this priority? By blowing the siren and horn together so that they can let everyone know that they are important people and you are supposed to give them way. That is exactly what QoS does, quality of service. So during traffic congestion in network, in your wire, right? In the network, if you have traffic congestion, the data which has a priority, like ambulance, right? Imagine this road as a wire. Imagine this road as a wire. And there are a lot of data. These square boxes that you see are a lot of data, right? And suddenly there is a data that needs to be sent urgently. So what you do, you give it a priority. We give priority in networking through the help of QoS or quality of service. Quality of service is a completely different topic, which I'm not going to discuss in detail right now. So understand, through this QoS, you are giving a special priority or a special entry. You can say that you're giving a special entry to this data so that it can move faster during congestion. Again, during congestion. This QoS or this priority will work only during congestion. If there is no congestion, or think from this perspective, if there is no traffic at all, if there are no vehicles on the road, why is this ambulance even going to blow the siren? right? There is no use of siren when there is no traffic. Correct? Similarly, there is no use of QoS if there is no congestion. So this QoS works only if there is congestion. Now, during congestion, QoS will work. The higher priority data will be given more priority during traffic congestion in the network. So when you have QoS enabled on a data, it will be marked. It will be marked in this QoS field. It will be marked in this QoS field. And since my data that I'm sending or receiving, whatever, does not have any priority, you can see it is 0, 0. If it was a priority, if it had some kind of priority, right? Let's say I am for example, hypothetical. Okay. I am a VIP person. Okay. Or I am working for some specialized government project. My data, if I capture my data, it will have some priority. We will see some kind of information over here. Okay. So it is also called as DSCP that you just saw. Okay. You can think of it as a QoS or TOS or DSCP, whatever. All right. So if you have some special priority given, it will be mentioned in this QoS. The total length. Now, the total length is including your options field and including your data field. What is the total length of your IPv4 header? So in interview, they ask you this question. What is the difference between header length and total length in an IPv4? Now you know the difference. Header length is the minimum size of your IPv4 header, and that is always 20 bytes. Whereas your total length constitutes your 20 bytes plus options field plus data field. Again, since these are variables, your data and your options. Again, it depends on what are the options you're using. It depends on how much data, what is the size of the data. It depends. So currently, the data that I am sending to Wireshark has a size of 55 bytes. In total, the IPv4 header is a size of 55 bytes. Clear? This is the difference between your header length and total length. Okay. Now, identification. The flags, that is RF, reserved flag, DF and MF, and fragmentation option. These three fields come into picture when you have fragmentation or when you have fragmentation or there is a problem with MTU. Okay, what is MTU? Maximum transmission unit. What is maximum transmission unit? Anyone?
The maximum data that we can send it on the link.
Correct. Okay. So MTU, let's say you have two routers, R1, R2, right? So the maximum data that it can send through this link, through that interface. Okay, maximum bytes of data that it can send through this link out, not receiving data, sending data. Okay, the maximum data that the router can send through this interface is called the MTU, maximum transmission unit. Okay, now let's assume 3 routers. Now please listen to this very carefully. Okay, I hope you guys have time. It's already 10:30. Okay, we'll take another 15 minutes. Is it okay?
Yes, yes.
Vivek, Tarun, are you okay if I take 15 more minutes?
Yes, sir.
This is important topic. That's better.
So by default on Cisco switches, the maximum transmission unit or your MTU is 1500 bytes. Okay, by default on Cisco switches. I'm not sure about other switches, but sorry, not other vendors, but on Cisco routers and switches, the maximum transmission unit is 1500 bytes. Okay. Now on R1, this is 1500. It can send a 1500 bytes of data in a single shot. On R2, let's say this is 500 only, meaning at any point of time, it can send only a 500 bytes of data in a single shot. Okay. Now, let's say R1 sent that data. Let's say R1 sent packet number 1, for example, which has a size of 1500 bytes. Okay. It is sent to R2. Now, this MTU comes into picture only when it is sending, not receiving. That is why I kept on saying MTU is the maximum transmission unit when the router is sending out, not receiving, sending out. So R2 here, it accepts the 1500 bytes of data. But when it is sending, it cannot send 1500 bytes of data, correct? It can send only 500 bytes of data in a single shot. So what it does, it will divide this 1500 bytes of data into 500 separate bytes of data. Okay, 500, 500, and 500. Okay, so 500 bytes of data, this becomes one IPv4 packet. 500 bytes of another data, this also becomes another IPv4 packet. 500 bytes of data, this also becomes another IPv4 packet. Now R2 sends this data to R3. Now the question, how is R3 going to identify that all these 500 bytes of data, are they single packets, or if it combines, it will get 1500 bytes of data? Again, let me say this question once again. The problem is with R3. R3 does not know that R2 has fragmented the packets. R3 does not know that R2 has fragmented the packets. So how is R3 going to identify that these 500, 500, 500, 3 different packets are basically the same packet? If R3 combines it together, it will basically see this original packet. How is R3 going to know that? Okay, for that purpose only, the identification field, the first field over here, the identification field, when R2 is sending this fragmented data. So what R2 is basically doing, R2 is actually fragmenting a bigger packet. It is fragmenting a bigger packet into 3 smaller packets. So when R2 is fragmenting the packets, it will put some identification mark to it. Let's say that identification mark is A, for example, A. Okay. Now when R3 receives it, it will read the identification marks on all these IPv4 packets. It will know that it will see this identification mark of A, and it will know that all these packets are similar packets or belong to the same big packet. Okay, so it keeps a note of it. 500, it will when it receives, it will collect it. 500, 500, 500, where the identification mark is A, and A. Now, the problem here is that to make, when R3 is going to combine these 3 packets together, R3 should be able to read it properly. Why is that necessary? You may think that, okay, 3 different packets with the same identification marks are received. Now all R3 needs to do is combine this together, make it into a single 1500 bytes of data and read it. Yes, it is as simple as that. But no, it is not as simple as that because there is no guarantee that these 500 packets, 500 bytes of data, 3 different 500 bytes of data are sent in a sequential manner. Again, I'm repeating, it is not necessary that these 3 different packets are sent sequentially. Let's say this is packet number 1, packet number 2, packet number 3. The data that is sent to 3 may be sent like 213 or 312 or 321 or 132, whatever. It may be sent like 123 also, but it may be sent randomly also. So how is R3 going to identify which is the first packet, which is the second packet, and which is the third packet? Okay, before I come to the solution, is everyone clear with the problem?
Yes.
Tarun, Vivek?
Yes, sir.
Yeah.
Yes,
Okay.
yes.
So the solution is this fragmentation offset. The solution is this fragmentation offset. Okay. So when R3, okay, when it receives this packet, it will use the fragmentation offset field. Okay, when R3 receives this packet, it will use the fragmentation offset field to rearrange these packets. Okay, so after using the fragmentation offset field, R3 will rearrange the packet in the sequential manner. Then it is going to combine these packets together and forms one big packet of 1500 bytes, the original data that was sent here. And this is how the identification field and the fragmentation offset fields are used in an IPv4 header. Clear?
Like I got it, but is there is no any rule, right? Like it has to divide 500 500 like that, no? Is there any, like for example, if R2 received data for 1600, it has to fragment like equally. It is not like that, right?
Not like that. You are absolutely right. For this, I will recommend I have a separate video, especially for this, only for this fragmentation and offset.
Okay. Okay.
Go watch my YouTube channel. There is a video for fragmentation and identification.
Okay, I will check that.
Just search that.
Okay.
I have explained how it actually works.
Okay.
How these two fields basically work. All right. So it is a bit tricky. It has a lot of mathematical calculations. Okay, so be ready with pen and paper when you are viewing that video. Okay, again, check my YouTube channel for fragmentation, or you can check my the website also under the free videos in all the languages. This is present in all the languages, Hindi, English, and Tamil. Okay, you can check this video, fragmentation and identification. How is it done?
Okay, I will check that. Yeah.
Okay,
Okay.
so your these 3 fields, reserved, don't fragment, and more fragment field, also comes into picture during fragmentation. So this complete row, right? This complete row is used or come into picture when you are actually fragmenting your packets into smaller packets. Okay. Now let's move on to the TTL, time to live. I think I do not have to go deeper into what TTL is. TTL, we know it is called as time to live, right? Time to live. On Cisco devices, it is 255, and on Windows devices, it is basically 128. So time to live is used between routers, okay, so that the packet never, packet is never looping in the network. So in layer 3, we do not have a protocol like spanning tree protocol, right, which will basically avoid the loops. In layer 3, you have something called as time to live. In IPv4, even in IPv6, you have time to live, right, which basically helps in avoiding that loop. So what happens when R1 is sending a data to R2, R2 decreases the time to live value by 1. So 255 minus 1, 254. When R2 forwards the data to R3, R3 will decrease that value to 253. When R3 forwards that value, that data to R1, R1 will decrease that to 252. Like that. So every time the data is forwarded to the next router, the TTL value is decremented by 1. Okay, 128 is for Windows. Okay, Windows machine. So when this TTL value is decremented by 1, and eventually, if it reaches the value 0, that packet is basically dropped and it stops looping in the network forever. This is why TTL is used to avoid the loops in the data. Sorry, to avoid loops in the network. The next is the protocol field. Protocol field is exactly the same as layer 2 type field. What was the layer 2 type field doing? Layer 2 type field was telling what kind of layer 3 packet is it carrying, or layer 3 data is it carrying. Is it an IPv4 data? Is it an IPv6 data? Or is it an R? Like that. So let me show you that on Wireshark. So in your Ethernet header type field, you can see it says it is carrying an IPv4 data. In IPv4 data, you have something called as protocol field. Protocol field tells what kind of layer 4 data is it carrying. In protocol field, it says the layer 4. In layer 2, it was basically what is layer 3 in protocol, what layer 4 data is it carrying. Is it a TCP, is it a UDP, etc. And here you can see it says it is carrying this IPv4 packet is carrying a UDP data. All right, so protocol field tells what kind of layer 4 data is it carrying. Then the last field is checksum field. Checksum field is equivalent to your FCS field in layer 2. The same thing, the same process. Okay, that whenever a router or a layer 3 switch is sending an IPv4 data, it will also do a checksum. The receiving data will also do the checksum calculation. If the checksum value is same, the data is accepted. If not, the data is discarded. All right. Any question with checksum and protocol? And we already know about these two fields, the destination IP and source IP. Options fields I'm not discussing. It's too lengthy and it's too confusing. Data, we already know what data is it carrying. Okay. So this was about your layer 2 and layer 2, especially the Ethernet header, and layer 3, the IPv4. All right. Any question? Srinivas, Vivek?
I don't have. I understood.
All right. Vivek,
No, sir.
yourself? All right. So with this, we have come to a conclusion of our class today.